Okay, so then there's a theoretical question of, great, these things work in practice. They're somehow relying on things not being the worst case. But can you prove a theorem that says when these will work well, when they won't work well, or explaining why they work well when they do? So one of the few examples where we actually have a theoretical understanding of why an algorithm works well is in the linear programming problem, which the example here has come to be called smooth analysis, which is due to Spielman and Teng. So the linear programming problem is a lot like the integer linear programming problem, except we no longer require the output to be an integer. So you have some matrix A, and now I'm actually going to give you two vectors, B and C. And the idea is you want to find a vector x such that A of x is less than or equal to B. And again, this means A of x is a vector, B is a vector. Each component of those vectors should obey this inequality. And you want it to maximize the dot product between x and C. So this is now an optimization problem. When you don't require x to have integer coordinates, this problem is no longer NP-complete. So the integer linear programming problem is NP-complete. The linear programming problem, where x can have, say, rational coordinates, or in reality it will have something like floating point coordinates, is actually in P. But before we knew that, there was an algorithm due to George Dantzig called the simplex algorithm. And this algorithm, although it actually is known not to run in polynomial time in the worst case, it's still one of the most efficient algorithms in practice for solving linear programming. And Spielman and Teng sort of gave us the theoretical understanding for why. And the answer is, while there are matrices A and vectors B and C where the simplex algorithm takes exponential time, what Spielman and Teng proved is that for any matrix A and vectors B and C, if you perturb them by an arbitrarily small amount, so you perturb each coordinate by some very small amount epsilon, you will get new vectors, say A prime, B prime, C prime, on which the simplex algorithm actually does run in polynomial time. So here's actually a theorem which takes advantage of this idea of the things which arise in practice aren't going to be the worst case, right? Because the worst case in this example is somehow some very thin space of all possible inputs. And so if you just perturb by epsilon, which will happen in reality, you get an example where the simplex method works really well. All right, so the simplex method is one example of a heuristic where we can prove something about it and it works well in practice. But in general, heuristics come in a few flavors. And the two that I really want you to be aware of are, the question is it guaranteed or not? And when I say it, I mean things like the speed, the correctness. And when I say guaranteed, I mean guaranteed by a theorem. So the question is, are they guaranteed? Is the speed of the heuristic guaranteed? Is the correctness? And you can also talk about things like completeness. So speed and correctness are fairly obvious. Completeness means works in all cases, right? You could have a heuristic that actually gives you the wrong answer in some cases, but maybe it will tell you that, right? So then it's still technically correct, right? It knows when it got it wrong. You can prove theorems about it. But some of the time it's allowed to tell you basically, sorry, I couldn't come up with an answer, right? So there are lots of different trade-offs between the kinds of guarantees you can get. And when you're using a heuristic, you should just be aware of which of the aspects of the heuristic are guaranteed and which aren't. If you're not aware, it can get you into real trouble because you could sometimes, for example, if you're using a heuristic that's not guaranteed to be correct, and also not guaranteed to be complete, it could give you a wrong answer without telling you, right? And if you use that answer and you go off and you use it for subsequent things, you could end up in real trouble. So it's important to know when you're using a heuristic, which of the aspects are guaranteed. Okay, so we started out talking about NP-complete problems, which are very hard, but there are lots of good heuristics in practice. I mentioned linear programming, which is not NP-complete, but there's actually an exponential time algorithm in the worst case that does well in practice. But now I want to talk about things where even in the worst case, the simple algorithm is somehow not good enough. So for this, I want to talk about graphs and linear algebra. So we said before that the way a graph is represented in a computer is often by its adjacency matrix, which is a matrix of zeros and ones, which says where there's a 1, meaning that, that the node corresponding to that row is connected to the node corresponding to that column. Okay. And once you have a matrix, you should immediately think like, oh, what kind of linear algebra things can I do with this matrix? And often there are lots of graph theoretic problems whose solutions are essentially look at the adjacency matrix and apply some tool from linear algebra. Now the problem with this is that most routines in linear algebra take something like n cubed time, where n here is, let's say, the number of nodes in your graph or the number of rows and columns in your matrix. So this is certainly polynomial. It's even a relatively small polynomial, but sometimes even small polynomials are not good enough. So for example, if you were analyzing the Facebook social network, so this is a graph where vertices are users of Facebook, and there's an edge between two people if they're friends on Facebook. Facebook has about 1.4 billion users, and the issue is 1.4 billion cubed is essentially 3 times 10 to the 27. And if you recall, that would mean this is about 3,000 years on the world's fastest supercomputer. Right? So n cubed in this case, just because your input is so large, is really not going to be practical. But the great thing is, for matrices that come from graphs, there's actually better linear algebra algorithms you can do. So very recently, in the past decade or so, several groups of researchers showed that you could do much better than this. So Spielman and Teng and Kudis and Miller showed that essentially for matrices coming from graphs, you can actually do linear algebra in order n time. Right? And this is what we like to see. You can't really do better than this because this means in order n time, you need that much time to at least read the input, right? So yeah, this could be some constant multiple of that, but it's only a constant multiple. So you really can't do a lot better than this. And on the Facebook social network, a few billion operations is really not a big deal. You can probably do it on your laptop. So it's also good to be aware of, when more specific algorithms could be used in your situation. So you might have had a graph problem and say, oh, I know I can apply linear algebra to graph problems. Let me apply the standard linear algebra techniques to my adjacency matrix. Well, if your adjacency matrix is big enough, that's going to be a problem. But if you knew about these algorithms, then you would know, oh, let me not apply the off-the-shelf linear algebra problems. Linear algebra algorithms. Let me instead apply the linear algebra algorithms that are essentially designed for my case, which are much better than the generic ones. Okay, so this is another example where we've actually been able to say something theoretically about how much better we can do in practice for lots of instances that actually arise. Right? If you're trying to do general linear algebra, you're still stuck with n cubed for the most part. Okay. But what happens when even the heuristics don't work? Even the sort of problem-specific algorithms aren't good enough for you. Right? This can happen. And here we go to the age-old trick in mathematics, which is change your problem. So the idea here is, say you had some optimization problem. Right? You're trying to solve traveling salesman or kidney donor matching or any of these thousands of NP-complete optimization problems. And the heuristics just aren't doing it for you. They're taking too long, or if it's an incomplete heuristic, maybe it's not even giving you an answer, or maybe it's giving you wrong answers, but you're able to check those so they're wrong, but whatever it is, it's just not working for you. So one way you can change the problem is to look for approximate solutions. And the idea here is you have some optimization problem, and instead of asking for the exact optimum, you just want to ask for something that's close to the optimum. right? And it doesn't have to be close to the optimum solution in the sense that it actually looks like the optimum solution. It just has to be close in that sort of the value you're optimizing should be close to the value of the true optimum. So the idea here is you talk about, say, a C approximation algorithm is one which guarantees that its output is within a factor of C of the true optimum. Okay, and you may wonder, how is this possible? How could it know that it's within a factor of C without actually knowing what the true optimum is, right? But this is sort of the beauty of the algorithmic paradigm and being able to prove theorems about these things is you can actually construct algorithms, oftentimes very simple algorithms, even for NP-complete problems, where it's actually quite easy to prove that it's within some constant factor of the optimum. And we'll see that in the next segment.